Physics has a problem it does not advertise. The deeper we look into the structure of reality, the more we find that it is not built to last. Every scale, from the smallest particle to the edge of the observable universe, contains something that can break. Not in a billion years, not in theory. Now. And most of it, we discovered by accident. Right now, as you're listening to this, roughly 10,000 particles from outer space are passing through every square meter of your body. Most of them go straight through. Some of them strike your DNA. And every single day, every single cell in your body takes about 40,000 impacts from radiation, chemistry, and its own metabolism. You do not feel it. A repair system older than any species on this planet fixes the damage in real time, around the clock, without asking your permission. It catches almost everything. Almost. That is just your body. Zoom out, and it gets worse. The magnetic field that protects this planet from the sun has weakened by 9% in 200 years. The sun itself releases bursts powerful enough to shut down civilization roughly once every few thousand years. More than half the asteroids large enough to level a city have not been found. The ground beneath one of America's most popular national parks has erupted 3 times, on a cycle that says it is overdue. Zoom out further. The galaxy contains hundreds of millions of invisible black holes that produce no light and no signal. The universe is being pushed apart by a force that makes up 68% of everything, and nobody knows what it is. The vacuum of space, the thing we call empty, may not be in its lowest energy state. If it drops, a bubble of new physics expands at the speed of light and rewrites the rules of matter. You cannot see it coming. You cannot outrun it. You would not even know. Every scale of reality, from the inside of an atom to the edge of the observable universe, contains a mechanism that can end everything. Not in theory, in the data. And the more precisely we measure, the worse the picture gets. This is not a list of worst-case predictions. This is what physics actually says about the structure of the world you live in. But first, we start at the bottom. The smallest thing there is. The particle. The brick. The foundation everything is built on. Because the foundation has cracks. In 1927, a German physicist named Werner Heisenberg published a 14-page paper that ended the mechanical universe. Until that point, physics operated on a simple promise. If you know the position and velocity of every particle, you can predict the future. Laplace said it in 1814. Newton's laws guaranteed it. The universe was a clockwork machine, and the only thing standing between us and total knowledge was better instruments. Heisenberg proved that better instruments will never be enough. Not because they are limited, because reality is. His uncertainty principle states that you cannot simultaneously know the exact position and the exact momentum of a particle. This is not a technical failure. It is not a gap in funding or a flaw in design. The information does not exist until the moment you measure it. Before you look, the electron is not somewhere. It is smeared across a cloud of probabilities. It has no single location. It has odds. Think about what that means for the floor beneath your feet. Every atom in that floor is built on particles that do not have definite positions. The solidity you feel, the resistance when you press your hand against a table, is not the hardness of matter. It is the electromagnetic repulsion between electron clouds that are themselves probabilistic. The foundation is not blurry to us, it is blurry to itself. And this is not a fringe interpretation. This is the most experimentally verified framework in the history of science. Every semiconductor, every laser, every MRI machine operates on the assumption that Heisenberg was right. The technology works. The universe is fuzzy at its core, but a fuzzy foundation is an old philosophical headache. The next problem is not philosophical, it is structural. Because in 1983, 2 physicists calculated that the most reliable object in the known universe might have an expiration date. The proton is the most durable object in the known universe. It has survived since the first microseconds after the Big Bang. Every atom of hydrogen in your body contains one. Every heavier element is built on stacks of them. Protons outlast stars. They outlast galaxies. Every textbook calls them stable. And for almost a century, no one questioned it. In 1983, Howard Georgi and Sheldon Glashow at Harvard proposed a framework called Grand Unified Theory. The idea is that the three fundamental forces of nature, electromagnetism, the strong nuclear force, and the weak nuclear force, are actually one force that split apart as the universe cooled after the Big Bang. The math is elegant. The predictions are specific. And one of those predictions is that the proton is not eternal. Grand unified theories give the proton a half-life of roughly 10 to the 34th years. That is a 1 followed by 34 zeros. It is 10 trillion times longer than the current age of the universe. That sounds safe, but your body contains 7 times 10 to the 27th protons. When you run the statistics on a number that large, the probability shifts. Somewhere in the water of your cells, in the calcium of your bones, a handful of protons may be decaying right now. Not in a billion years. Now. Deep inside Mount Ikanoyama in Japan, a detector called Super-Kamiokande waits for proof. 50,000 tons of ultra-pure water surrounded by 11,000 photomultiplier tubes. Each tube is watching for a single flash of light, the signature of one proton giving up. 20 years of watching. Nothing yet. But the equations have not changed their mind. So the most reliable building block in existence carries a countdown. It is written in a font too small for any instrument to read. But the math insists it is there. And if the bricks are mortal, the space between the bricks has a far more urgent problem. In 1928, a Soviet physicist named George Gamow was trying to solve a problem that had embarrassed nuclear physics for years. Uranium is radioactive. Its nucleus spits out alpha particles. But when you calculate the energy of those alpha particles, they do not have enough power to escape the nucleus. The nuclear force holds them in like a ball trapped inside a well. The walls of the well are too high. The ball doesn't have the energy to jump over. And yet, the ball gets out. Gamow showed that in quantum mechanics, a particle does not need to climb over a barrier. It can pass through it. Not by breaking the wall, not by finding a gap. It simply appears on the other side with a probability that is small but never zero. This is quantum tunneling. The particle does not experience the wall. From its perspective, it was inside and then it was outside. There is no moment of transition. This sounds like a curiosity. It is not. The scanning tunneling microscope, one of the most precise imaging tools ever built, works because electrons tunnel between a needle tip and a surface. Every transistor in the processor running your phone works because charge carriers tunnel through insulating barriers. This mechanism is not speculative. It is engineering. It is in your pocket. Now take that mechanism and scale it up. Not to an electron passing through an insulating layer. Not to an alpha particle leaving a uranium nucleus. Scale it to a quantum field that fills every cubic centimeter of the universe. Scale it to the vacuum itself. Because in 1980, two physicists asked a very specific question. If the vacuum of space is not in its lowest energy state, can it tunnel to a lower one? And the answer was the most dangerous sentence in theoretical physics. In quantum field theory, a vacuum is not empty space. It is the lowest energy state of a field. Every point in the universe is soaked in fields. The electromagnetic field, the Higgs field, the gluon field, and the energy level of each field determines the rules of physics. The constants of nature, the mass of particles, the strength of forces are set by where these fields sit in their energy landscape. In 1980, Sidney Coleman at Harvard and Frank De Luccia at Stanford published a paper with a title that read like a legal notice and a conclusion that read like an expiration notice for the cosmos. They asked whether the vacuum we live in is a true vacuum, the absolute lowest point, or a false vacuum, a local minimum that only looks like the bottom. The difference is everything. A true vacuum is a ball at the bottom of a valley. You can kick it, shake it, hit it with a hammer. It rolls back down. It is stable by definition. A false vacuum is a ball sitting in a small dip on the side of a mountain. It looks stable. It stays put for as long as nobody touches it. But the dip is not the bottom. Below it, the slope drops away into a much deeper valley. And quantum mechanics says you do not need to kick the ball over the rim. It can tunnel through. Coleman-De Luccia calculated what happens next. A bubble of true vacuum forms at the tunneling point. Inside that bubble, the fields settle to their real minimum. The constants change, the physics changes, the bubble wall expands outward at the speed of light, converting everything it touches into the new state. There is no force in the universe that can stop it. There is no signal that outruns it. Everything inside the bubble obeys different rules, and in those rules, atoms may not hold together. But in 1980, this was pure math. Nobody knew which vacuum we live in. That answer required a specific particle, found 32 years later. On July 4th, 2012, two independent teams at the Large Hadron Collider announced the discovery of the Higgs Boson. The room at CERN erupted. Peter Higgs, who had predicted the particle in 1964, wiped tears from his eyes. It was the most celebrated moment in modern physics, and buried inside the data was a number that changed the meaning of the celebration. The mass of the Higgs boson was measured at approximately 125.25 giga-electron volts. To anyone outside of physics, that number means nothing. To anyone inside, it is the worst possible answer. Below 115 giga-electron volts, the mathematics guarantee that the vacuum of the universe is absolutely stable. The ball is at the bottom. Nothing can push it out. Above roughly 130 giga-electron volts, the vacuum is unstable. The ball has already rolled. The universe would not have survived long enough to produce a planet, let alone a physicist. But 125 giga-electron volts sits in a narrow corridor between those two walls. Physicists call it the metastable zone. The ball is in the dip. The dip is not the bottom. This means the vacuum of space, the substrate on which all matter and all energy and all chemistry and all life depend, is not guaranteed to last. A sufficiently energetic quantum event, a fluctuation at the right frequency in the right place, could nucleate a bubble of true vacuum. That bubble would expand at the speed of light. Inside it, the binding constants shift. Protons may not hold together. Electrons may not orbit nuclei. Chemistry becomes impossible. Biology becomes impossible. And you would never see it coming. The bubble travels at exactly the speed of light. The photon that could warn you arrives at the same instant as the wall that erases you. There is no before. There is no warning. There is only a boundary moving through space, rewriting the laws of nature as it goes. One moment you exist. The next moment, the rules that allow you to exist have been replaced. The most precise measurement in the history of particle physics told us exactly where we stand. We are not at the bottom. We are in the dip. And the mountain below is very, very deep. So the smallest components of reality are fuzzy, temporary, and sitting on a trapdoor. But these are abstractions. Particles and fields and vacuum states. Let's talk about something closer. Let's talk about the thing made of those particles. Your body. Because your body is under assault right now. And it has been under assault since the moment you were born. Every second, the sun and distant collapsed stars spray the solar system with high-energy particles. Protons mostly accelerated to nearly the speed of light by supernova shockwaves and magnetic fields across the galaxy. When these cosmic rays hit the upper atmosphere, they shatter nitrogen and oxygen nuclei and produce a shower of secondary particles. Moons, roughly 10,000 of them per square meter per minute at sea level. They pass through your roof. They pass through concrete. They pass through bone. Most of them fly straight through your body without touching anything. But some of them collide with molecules inside your cells, and when a high-energy particle hits a strand of DNA, it can snap the double helix like a wire cut in two. In 2017, a team led by Francis Cucinotta at the University of Nevada quantified the total damage load. From all sources combined, cosmic rays, background radiation, metabolic byproducts, oxidative stress, every single cell in your body sustains approximately 40,000 DNA lesions per day. 40,000 per cell per day. Your body contains roughly 37 trillion cells. The math is staggering, and yet you function. A molecular repair system older than multicellular life reads the damage, cuts out the broken segments, and rebuilds them using the complementary strand as a template. It works around the clock. It catches almost everything. Almost. Because every once in a while, a repair enzyme misreads a break, or skips it, or patches it wrong. A single uncorrected error in a single gene in a single cell is the difference between a normal Tuesday and a malfunction that will not stop growing. The bombardment is constant. The repair is imperfect. And the margin between health and catastrophe is one missed stitch in 40,000. Repeated 37 trillion times a day. Radiation is an assault from outside. The next threat comes from inside the blueprint. It is not damage. It is design. In 1961, an anatomist named Leonard Hayflick at the Wistar Institute in Philadelphia noticed something that cell biologists had been ignoring for decades. Cells do not divide forever. He grew human fetal cells in culture and watched them. They divided 50 times, sometimes 60, sometimes 70. Then they stopped. Not because they ran out of nutrients, not because the environment changed. They simply reached a limit and shut down. The cell was alive, but it refused to copy itself. Hayflick had discovered a countdown built into the machinery of life. The mechanism was found later. At the tip of every chromosome sits a repeating sequence of DNA called a telomere. It does not code for anything. It is a protective cap, like the plastic tip on a shoelace. Every time a cell divides, the copying machinery cannot replicate the very end of the strand. A small piece of telomere is lost. Division by division, the cap shortens. When it gets too short, the cell triggers a program called senescence. It stops dividing. It changes shape. It begins secreting inflammatory signals that damage the tissue around it. Eventually it shuts down or is cleared by the immune system. And here is the part that should keep you up at night. In 2009, Elizabeth Blackburn won the Nobel Prize for discovering telomerase, an enzyme that can rebuild telomeres. The key exists. The lock can be reopened. But in the vast majority of your cells, the gene that codes for telomerase is switched off. Your body possesses the molecular tool to prevent its own aging, and it chooses not to use it. The only cells that routinely activate telomerase are rogue cells, cells that have broken the rules. That is what makes them immortal. So the body knows the recipe for indefinite repair. It keeps the recipe locked in a drawer, and the only cells that break into the drawer are the ones trying to shut you down. So the body is bombarded from outside and programmed to decay from inside. But both of these threats operate on the timescale of a single life. 70 years, 80, maybe 100 if the repair systems hold. The next force does not care about your lifespan. It is older than biology. It is older than chemistry. It has been running since the first fraction of a second after the Big Bang, and it has never once reversed direction. In 1865, a German physicist named Rudolf Clausius coined a word that would become the most depressing term in all of science: entropy. The second law of thermodynamics states that in any closed system, entropy always increases. Disorder grows, gradients flatten, hot things cool, cold things do not spontaneously heat up. An egg falls off the counter and shatters on the floor. The pieces never reassemble and jump back onto the counter. You know this intuitively. You have known it since childhood. What you may not know is that this law is absolute. It has no exceptions. It is the only law of physics that tells you which direction time moves. Life is a local violation of this law. An organism takes disordered raw materials, amino acids, sugars, minerals, and assembles them into spectacularly ordered structures. Proteins fold, cells organize, organs differentiate. A fertilized egg becomes a human being in 9 months, and every step of that process moves against the current of entropy. But it does not break the law. It borrows. Every ounce of order that life creates is paid for by dumping a larger amount of disorder into the environment. Heat, waste, carbon dioxide. The total entropy of the system always goes up. Life is not swimming against the river. Life is running on a treadmill that is bolted to a raft that is drifting downstream. Stop feeding the treadmill, stop eating, stop breathing, and entropy collects its debt in weeks. The structures unravel, the proteins denature, the cell membranes dissolve, the organism returns to equilibrium. Dust. Entropy is not a threat that might happen. It is a force that is happening right now, in every atom of your body, and it does not get tired. So entropy guarantees that every ordered structure eventually falls apart. Life fights it for a while and loses. But there is a larger question behind the biology. If life can emerge from chemistry, and chemistry can emerge from physics, and the universe has been running for 13.8 billion years across hundreds of billions of galaxies, each with hundreds of billions of stars, then the number of chances for life to appear somewhere is so large, it loses meaning. Trillions of dice rolled trillions of times, and yet, when we listen, we hear nothing. In 1950, during a lunch break at Los Alamos National Laboratory, the physicist Enrico Fermi was talking with colleagues about flying saucers and interstellar travel. He did a quick back-of-the-envelope calculation and asked a question that has haunted science ever since. Where is everybody? The galaxy is old enough and large enough that even at slow speeds, a single spacefaring civilization could colonize every star system in a few million years. A blink in cosmic time. But there are no signals, no probes, no megastructures blocking starlight. The sky is silent. In 1998, the economist Robin Hanson put a name to the silence. He called it the Great Filter. Somewhere between non-living chemistry and interstellar civilization, there is a wall. A stage so difficult, so improbable, so final, that almost nothing gets through it. The filter is either behind us or ahead of us. If it is behind us, then the hard step was something we already passed. Maybe it was the origin of life itself, or the jump to eukaryotic cells, or the development of intelligence. We got lucky. If the filter is ahead of us, then civilizations routinely reach our stage and then are ended by something we have not encountered yet. And here is the part that makes every new discovery of a habitable exoplanet a little more unsettling. Every time the Kepler telescope or the James Webb Space Telescope finds a rocky world in a star's habitable zone, the number of places where life could have started goes up. And the more places where life could have started, the more terrifying the silence becomes. Because if the ingredients are common and the kitchen is everywhere and nobody else is serving dinner, then something is shutting down the restaurant. The filter is real. The question is where it sits, and we do not have enough data to know whether we have already passed it or whether it is waiting for us around the next corner. But the Great Filter asks about civilizations. The deeper question is whether life had any right to exist in the first place. Not biologically, physically. Whether the universe, as a structure, was ever supposed to produce something that looks back at it. In 1953, the British astrophysicist Fred Hoyle was working on stellar nucleosynthesis, the process by which stars forge heavier elements inside their cores. He hit a wall. Carbon, the backbone of every organic molecule, should not exist in any meaningful quantity. The nuclear reactions that build carbon from helium require a very specific resonance, a precise energy level in the carbon-12 nucleus that amplifies the reaction rate by orders of magnitude. Without that resonance, carbon is a trace element. No carbon, no organic chemistry. No organic chemistry, no life. Hoyle predicted the resonance level at 7.65 mega-electron volts. He told the experimental physicists what to look for. They found it exactly where he said it would be. Hoyle later wrote that it looked as though someone had been monkeying with the physics, but Hoyle was looking at one constant. The full picture is worse. The strong nuclear force, which holds protons and neutrons together inside the nucleus, has a coupling constant of approximately 0.1. Shift it up by 4% and the duproton becomes stable. Hydrogen fuses instantly. Stars cannot burn slowly enough to sustain chemistry. Shift it down by 4% and deuterium is unstable. Stellar nucleosynthesis stops. No heavy elements, no planets, no us, gravity. Shift the gravitational constant by 1 part in 10 to the 40th, and stars either collapse immediately or never ignite. The cosmological constant, the energy density of empty space, is measured at roughly 10 to the minus 122 in Planck units. Steven Weinberg showed in 1987 that if this value were larger by a factor of 100, gravity could not hold galaxies together. If it were negative, the universe would have recollapsed in millions of years. Roger Penrose calculated the probability of the initial entropy conditions of the Big Bang landing in the range compatible with structure formation. 1 in 10 to the power of 10 to the 123. That is not a number. That is a monument to how improbable you are. The anthropic principle says we observe these values because in a universe with different values, there is no one to observe. This is technically true. It is also not an explanation. It is a shrug. The numbers are what they are. Nobody knows why. And the margins are thin enough to make you wonder whether the whole arrangement is a lucky accident, a selection effect, or something else entirely that physics does not yet have a name for. So at the scale of particles, the foundation is blurry and temporary. At the scale of biology, the body is under siege from the outside and wired to fail from the inside. At the scale of probability, life should not be here at all. But here we are, standing on a rock orbiting a middle-aged star. And for most of human history, that rock felt safe. Solid ground, thick atmosphere, a magnetic field wrapping the planet like an invisible cocoon, deflecting the worst of what the sun throws at us. That cocoon is failing. The Earth's magnetic field is generated by convection currents in the liquid iron outer core, roughly 3,000 kilometers below your feet. It extends tens of thousands of kilometers into space, forming the magnetosphere, a bubble that catches the solar wind and channels it around the planet. Without it, charged particles from the sun would strip away the atmosphere molecule by molecule. We know this is not theoretical because we can see the result. Mars once had a magnetic field. It lost it roughly 4 billion years ago. Today, Mars has an atmosphere thinner than the air on top of Everest. The solar wind took the rest. In 2013, the European Space Agency launched 3 satellites called Swarm to map the Earth's magnetic field in high resolution. The data confirmed what ground stations had been tracking for 2 centuries. The field is weakening. Over the last 200 years, the overall strength has dropped by approximately 9%. That is fast. Geologically, that is a sprint. But the decline is not uniform. In a region stretching from southern Africa to South America, the field is already critically weak. It is called the South Atlantic Anomaly. Inside this zone, the magnetic protection is so thin that satellites passing through it routinely shut down sensitive instruments to avoid radiation damage. The International Space Station reports higher radiation readings every time it crosses the anomaly. Astronauts have described seeing flashes of white light behind their closed eyelids, caused by cosmic rays passing through their eyes and striking their retinas. The shield is not gone, but it has a hole, and the hole is growing. A weakening field would be concerning enough on its own. But the geological record tells us this is not just a decline, It may be a prelude to something far more dramatic. The Earth's magnetic field has flipped hundreds of times in the planet's history. North becomes south. South becomes north. The compass needle points the opposite direction. And in between, the field does not simply rotate, it collapses into chaos. The evidence is written in a volcanic rock. When lava cools, iron minerals inside it align with the ambient magnetic field and freeze in place like tiny compass needles set in stone. By drilling cores from ancient lava flows and reading the orientation of those minerals layer by layer, geologists have reconstructed a timeline of magnetic reversals stretching back hundreds of millions of years. The pattern is irregular, but persistent. The last full reversal occurred approximately 780,000 years ago. It is called the Brunhes-Matuyama boundary. The average interval between reversals over the past few million years is roughly 450,000 years. We are 330,000 years overdue. During a reversal, the dipole field weakens to roughly 10 to 20% of its normal strength. Multiple magnetic poles appear simultaneously across the surface. The neat protective bubble deforms into a chaotic patchwork of weak spots and temporary loops. In 2018, a team at the University of Leeds modeled the consequences for the biosphere. During the transition period, which can last anywhere from 200 to several thousand years, solar and cosmic radiation reach the surface at levels the biosphere has not experienced since the field was last down. The ozone layer takes direct hits. UV exposure spikes. Every species that navigates by magnetic field, birds, sea turtles, bees, salmon, loses its compass. The swarm data showing the current weakening, the expanding South Atlantic Anomaly, the appearance of a reversed polarity patch under southern Africa. These are not random fluctuations. They match the pattern that precedes a flip. We do not know when. We do not know how fast. But the rock remembers what happens when the shield drops. And the clock says we are late. But a magnetic reversal unfolds over centuries. The sun can do its damage in 8 minutes. That is the time it takes light to travel from the solar surface to your skin. And what comes with that light, occasionally, is something far worse than photons. On the morning of September 1st, 1859, a British astronomer named Richard Carrington was sketching sunspots through his telescope at his private observatory in Redhill, Surrey. At 11:18 a.m., he witnessed something no astronomer had ever recorded. 2 points of intensely white light erupted from the surface of a sunspot group. They were so bright, they overpowered the filtered image of the sun itself. The flare lasted about 5 minutes. Carrington noted the time and moved on. 17 hours later, the sky lit up. Aurora Borealis, normally confined to polar latitudes, appeared over the Caribbean, over Colombia, over Central Africa. Telegraph systems across Europe and North America failed simultaneously. Operators reported sparks leaping from their equipment. In some stations, the machines continued to transmit and receive messages after being disconnected from their batteries, powered entirely by the electric current induced in the wires by the geomagnetic storm. Paper caught on flames. The global telegraph network, the most advanced communication system on the planet, was coming apart at the seams. That was 1859. The world ran on steam and copper wire. In 2012, the sun discharged again. A coronal mass ejection of comparable magnitude to the Carrington Event erupted from the solar surface on July 23rd. It crossed the orbit of the Earth. We were not there. The planet had moved past that point in its orbit 9 days earlier. 9 days. Daniel Baker at the University of Colorado analyzed the event and estimated that a direct hit would have caused between $1 and $2 trillion in damage. Electrical grids across the developed world would have been wrecked. Not disrupted. Wrecked. High voltage transformers take months to build and years to replace at scale. Baker's projection for full recovery was 4 to 10 years. We missed it by 9 days. The sun did not miss. We moved. But the Carrington Event, as violent as it was, is not the ceiling. It is not even close. For most of the 20th century, we assumed the Sun was a calm, predictable star. Sunspots come and go in 11-year cycles. Flares erupt and fade. The baseline seemed safe. Then we pointed the Kepler Space Telescope at 83,000 stars, similar to the Sun, and watched them for 4 years. In 2012, Kazunari Shibata at Kyoto University published the results. Sun-like stars produce superflares, events 100 to 1,000 times more powerful than the Carrington Event. They happen roughly once every 2,000 to 3,000 years per star. This is not a theoretical extrapolation. This is a census. Kepler watched tens of thousands of solar twins and counted the flashes. The statistics are solid, and the geological record on Earth confirms it. In 2012, Fusa Miyake at Nagoya University found a sharp spike in carbon-14 concentrations in tree rings dating to 774 AD. Carbon-14 is produced when high-energy particles from space hit nitrogen atoms in the upper atmosphere. A sudden spike means a sudden flood of radiation. The magnitude of the 774 AD event, now called the Miyake event, was estimated at 50 to 100 times the Carrington event. Ice cores from Greenland and Antarctica show the same signal at the same date. It was global. It was fast. And in 774 AD, there was nothing to break. No power grid, no satellites, no internet, no supply chain. Today, a Miyake-class event would not just disrupt infrastructure. At 100 times Carrington, the geomagnetically induced currents in long-distance power lines would be strong enough to melt transformer windings across entire continents. Satellites in low Earth orbit would be bathed in radiation levels that exceed their shielding. GPS would go dark. Communications would fail. The cascade would be total. Not because the Sun did something unusual, because the Sun did something it does regularly, on a schedule we can now read in the rings of ancient trees. The last Miyake event was 1,250 years ago. The average interval is 2,000 to 3,000 years. The next one is not a question of if. So the Sun discharges on a schedule we can read but cannot control. At least we can see the Sun. The next object arrived without a sound, without a signal, and without a single telescope on the planet knowing it existed until it was already inside the atmosphere. February 15th, 2013, 9:20 a.m. local time, Chelyabinsk, Russia. A rock 20 meters across entered the atmosphere at roughly 19 kilometers per second, traveling from the direction of the Sun. No observatory detected it. No early warning system flagged it. No satellite tracked its approach. It was invisible against the solar glare. At an altitude of approximately 30 kilometers, the asteroid burst apart. The airburst released energy equivalent to 500 kilotons of TNT. The shock wave propagated outward at supersonic speed. It shattered windows in over 7,000 buildings across 6 cities. 1,500 people were injured, most of them by flying glass. Dashboard cameras across the region recorded a second sun blooming in the morning sky, bright enough to cast sharp shadows on the snow. On that same day, astronomers around the world were watching a completely different asteroid. 2012 DA14, a 50-meter object that passed within 27,700 kilometers of the Earth, closer than the orbit of geostationary satellites. The entire planetary science community had its eyes on DA14. Nobody saw the Chelyabinsk rock. It came from the opposite side of the sky. 2 separate objects, 2 separate trajectories, one day. A coincidence that the laws of orbital mechanics do not care about. The Chelyabinsk impactor was 20 meters. It broke windows and injured hundreds. A city ender starts at 140 meters. A civilization ender starts at 1 kilometer. And the thing that made Chelyabinsk invisible, the Sun, is still in the way. Chelyabinsk was not an outlier. It was a reminder of how little we actually see. The solar system is full of rock, and most of it has not been catalogued. As of 2024, NASA's Center for Near-Earth Object Studies has identified approximately 34,000 near-Earth objects. Of those, about 10,500 are 140 meters or larger, the threshold at which an impact transitions from a local disaster to a regional catastrophe. But the estimated total population of NEOs at that size is roughly 25,000, which means more than half have not been found. They are out there. They are orbiting. And we do not know where they are. The problem is not laziness. It is physics. Ground-based telescopes can only observe objects that are illuminated by the sun and positioned against the dark background of space. An asteroid approaching from the sunward side, like the Chelyabinsk impactor, is washed out by solar glare. It is invisible. A dark asteroid with a low albedo, a surface that absorbs most of the light that hits it, reflects so little that even a large one can pass undetected at relatively close range. These are not edge cases. These are structural blind spots in the observation system. NASA's answer is a space-based infrared telescope called NEO Surveyor. In infrared, an asteroid does not need to reflect sunlight. It glows with its own heat. NEO Surveyor is designed to find the dark ones, the sunward ones, the ones that ground telescopes miss. But as of 2024, it has not launched. Current projections place the launch no earlier than 2028. Until then, the blind spot remains. Half the sky is a question mark, and the window between detection and impact for a previously unknown object can be vanishingly short. For a rock on a direct approach from the sunward side, the warning time could be measured in days. For a fast-moving comet from the outer solar system, it could be months. For a dark asteroid on an unfortunate trajectory, it could be 0. The first sign of its existence would be the flash. So the sky has charged mechanisms and blind spots. The sun discharges on a schedule. Rocks come from directions we cannot see, but at least these threats come from outside. The next one is already here. It is under the ground, and it has done this before. 74,000 years ago, on the island of Sumatra, a volcanic system called Toba erupted. It was not a normal eruption. It measured VEI8 on the Volcanic Explosivity Index, the maximum rating. The eruption ejected approximately 2,800 cubic kilometers of material into the atmosphere. For comparison, Mount St. Helens in 1980 ejected 1 cubic kilometer. Pinatubo in 1991 ejected 10. Toba ejected 2,800. Sulfuric acid aerosols reached the stratosphere and spread across the globe. They formed a reflective blanket that blocked incoming sunlight. Global surface temperatures dropped by an estimated 3 to 5 degrees Celsius. Some models suggest the cooling was even more severe in continental interiors. Vegetation collapsed. Food chains collapsed. A volcanic winter descended on the planet and did not lift for 6 to 10 years. The genetic evidence tells the rest of the story. Analysis of mitochondrial DNA suggests that around the same period, the global population of Homo sapiens crashed to somewhere between 3,000 and 10,000 breeding individuals. This is called a genetic bottleneck. Every human alive today carries DNA that passed through that filter. The diversity we lost in that crash is gone forever. Entire lineages, entire branches of the human family tree were pruned to nothing. 3,000 to 10,000 people on the entire planet. That is not a civilization. That is a small town. One eruption took a species that had survived ice ages and predators and drought and reduced it to the population of a single neighborhood. And Toba is not unique. It is not even the most recent system capable of doing it again. Beneath the Yellowstone National Park, one of the most visited landscapes in the United States, sits a magma chamber estimated at 46,000 cubic kilometers. It is not a volcano in the way most people picture one. There is no cone, no visible crater. The caldera is so large, roughly 70 by 45 kilometers, that it is invisible from the ground. You only see it from orbit. Yellowstone has erupted 3 times at the supervolcano scale. 2.1 million years ago, 1.3 million years ago, 640,000 years ago. The intervals are not exact, but the average is roughly 600,000 to 700,000 years. The last eruption deposited a layer of ash called the Lava Creek Tuff across most of the western United States. In some areas, the deposit is meters thick. The eruption was classified VEI8, the same scale as Toba. The United States Geological Survey monitors Yellowstone continuously. Seismometers, GPS stations, satellite radar, and ground deformation sensors feed data into models that track the rise and fall of the magma body in real time. The USGS estimates the probability of a super eruption in any given year at approximately 1 in 730,000. That sounds remote, and it is. But probability is not a guarantee of safety. It is a description of ignorance. We do not know when, we know what. If Yellowstone erupts again at the VEI8 scale, the immediate impact zone covers everything within a roughly 60-kilometer radius. Pyroclastic flows, clouds of superheated gas, and rock moving at hundreds of kilometers per hour sterilize the landscape. Beyond the blast zone, ashfall buries the surrounding region. USGS models show a layer of ash up to 3 meters deep within 500 kilometers. Major cities, Denver, Salt Lake City, are inside that radius. Agriculture across North America is functionally gone. Crops cannot grow through ash, livestock cannot breathe it. The global effects mirror Toba. Sulfuric aerosols block sunlight. Temperatures drop by 5 to 10 degrees Celsius for a decade or more. Global food production collapses. Supply chains that depend on North American grain exports collapse with it. The most visited national park in the country. Families posing in front of Old Faithful. Gift shops selling stuffed bison. And directly underneath, a system that has ended the world 3 times and will, at some point, do it again. So the planet carries its own arsenal. The crust can split. The shield can drop. The sun can discharge. Rocks come from angles we cannot cover. But all of this operates within our neighborhood. The solar system, a tiny pocket of gravitational influence around one ordinary star. The next scale makes our neighborhood look like a grain of sand on a beach that stretches beyond the horizon. And on that beach, there are mechanisms that make the sun look like a match. In 1967, a network of American government satellites called Vela was orbiting the Earth. Their mission was simple and classified: detect unauthorized high-energy tests in space that would violate the Partial Test Ban Treaty. The satellites carried gamma-ray detectors tuned to the specific flash of such an event. On July 2nd, Vela 4 registered a burst of gamma radiation. It did not match the expected signature. It was too long, too bright, and it came from the wrong direction. It came from deep space. The data was classified for 6 years. When it was finally published in 1973, it opened a mystery that took another 2 decades to solve. For years, astronomers debated the distance. If the bursts were nearby, inside the Milky Way, they were interesting but manageable. If they were far away, they were staggering. In 1997, the Italian-Dutch satellite Beppo-Sax detected a gamma-ray burst, and for the first time captured its fading afterglow in X-ray light. The afterglow allowed astronomers to pinpoint the host galaxy. The distance was measured in billions of light years. The burst was cosmological, and the energy implied by that distance defied comprehension. A single gamma-ray burst releases more energy in a few seconds than the sun will produce in its entire 10 billion year lifetime. That energy is not radiated in all directions equally. It is focused into 2 narrow jets, like the beams of a lighthouse. If you are in the path of the jet, the intensity is beyond anything else in the observable universe. If you are not in the path, you see nothing. A focused beam that either hits you with the power of an entire stellar lifetime or misses you completely. Billions of light years sounds safe. It sounds like someone else's problem. But gamma-ray bursts do not only happen at the edge of the observable universe. They happen inside galaxies. They happen in the Milky Way. And the source does not need to be close to be catastrophic. In 2004, Adrian Mellott and Brian Thomas at the University of Kansas published a model that calculated the biological impact of a gamma-ray burst at a distance of 6,000 light-years. Close by cosmic standards, but still far enough that the star responsible would be an unremarkable dot in the sky. The result was not subtle. Within seconds of the jet reaching the Earth, the gamma radiation would interact with nitrogen and oxygen in the upper atmosphere and produce massive quantities of nitrogen oxides. These compounds are ozone eliminators. Mellott's model showed that a single burst at that range would strip 30 to 50% of the ozone layer instantly. The recovery time would be measured in years. During that window, ultraviolet radiation from the sun would reach the surface at biologically unsurvivable levels. Marine ecosystems in shallow water would collapse. Terrestrial organisms without shelter would receive terminal doses. Mellott and Thomas proposed a candidate event, the Ordovician Silurian extinction, roughly 450 million years ago, the second largest mass extinction in the history of Earth. 85% of marine species wiped out. The pattern of the extinction, preferential elimination of organisms in shallow water and at high latitudes, is consistent with an ozone collapse triggered by a GRB. The case is not closed, but the physics fits, and the source does not have to be hypothetical. WR104 is a binary star system in the constellation Sagittarius, roughly 8,000 light-years from Earth. One of the stars is a Wolf-Rayet, a massive unstable object in the final stages before collapse. When it goes, it may produce a gamma-ray burst. The axis of rotation, the direction the jets would aim, has been studied. The data is inconclusive. Some measurements suggest the axis points within degrees of our solar system. Others suggest we are off to the side. The uncertainty is not comforting. We do not control the aim. So a gamma-ray burst is a visible event, even if it arrives without warning. A flash of energy from a collapsing star. At least we can name the source. At least we can point to WR104 and say that star might be dangerous. The next threat offers no such courtesy. It produces no light. It sends no signal. It cannot be seen by any telescope designed to detect photons, and there may be 100 million of them drifting through this galaxy right now. In 2022, 2 independent research teams announced a result that had been pursued for decades. Kailash Sahu at the Space Telescope Science Institute and Casey Lamb at UC Berkeley both confirmed the first detection of an isolated stellar mass black hole. The object, catalogued as OGLE 2011 BLG 0462, was found not by its light, because it produces none, but by the way its gravity bent the light of a background star passing behind it. This technique is called Gravitational Microlensing. The background star brightened in a specific predictable curve as the black hole crossed the line of sight. From the shape of that curve and the duration of the event, the teams calculated a mass between 1.6 and 7.1 solar masses. The object is roughly 5,150 light-years away, moving at about 45 kilometers per second relative to the surrounding stars. One black hole, found by accident, because a background star happened to be in the right place at the right time. The detection method only works during the alignment. Before and after, the object is invisible again. Theoretical models estimate the Milky Way contains between 100 million and 1 billion isolated stellar mass black holes. These are the remnants of massive stars that collapsed at the end of their lives, but were not captured into binary systems. They orbit the galactic center like every other star, but they carry no beacon, no accretion disk, no jets, no radiation. They are gravitational ghosts wandering the galaxy in complete silence. We found one. We have 100 million to go, But a black hole drifting between stars is, statistically, a remote risk. The distance between stars in the Milky Way is so vast that the probability of one passing close enough to the inner solar system to disrupt planetary orbits is negligible on human timescales. So why does it belong on this list? Because the black hole does not need to come close, it just needs to pass through the neighborhood. In 1999, John Matese at the University of Louisiana published a model examining the gravitational effects of a stellar mass black hole transiting the Oort cloud. The Oort cloud is the outermost shell of our solar system, a vast sphere of trillions of frozen bodies, comets and ice, extending roughly 2 light-years from the Sun. It is loosely bound. The objects inside it are barely held by the Sun's gravity. They orbit on the edge of falling away entirely. A passing mass disrupts that balance. Matese's simulations showed that a single pass by an object of 5 to 10 solar masses through the outer Oort cloud would gravitationally perturb billions of cometary orbits. Some would be ejected from the solar system entirely. Others would be deflected inward toward the Sun and the inner planets. The bombardment would not arrive all at once. It would unfold over millions of years, a slow rain of ice and rock redirected from the deep freeze of the outer solar system into crossing orbits with Earth, Mars, Jupiter. We would see the comets eventually, bright tails appearing in the sky, but the trajectories would be wrong. They would come from directions that the standard models do not predict. By the time an astronomer traced the orbits backward to their origin point, the black hole would already be gone. It would have passed through, nudged the ice and continued into the dark at 45 kilometers per second. No light, no heat, no trace, no return address. A stone thrown 10 million years ago arriving as a slow cascade of ice that looks, to anyone without the full data, like random bad luck. So invisible objects drift through the galaxy, and their damage arrives long after they leave. These are stochastic risks, dice rolls. But the next event on this list is not a probability. It is a certainty measured to the decimal point. In 2012, a team led by Roland van der Marel at the Space Telescope Science Institute used the Hubble Space Telescope to measure something that had never been measured directly before: the sideways motion of the Andromeda galaxy. Astronomers had known for over a century that Andromeda is moving toward us. The blue shift in its light confirmed that much, but blue shift only tells you the speed along the line of sight. It does not tell you whether the object is aimed directly at you or whether it will pass to the side. The difference between a head-on collision and a near miss depends entirely on the tangential velocity. The sideways component, which for a galaxy 2.5 million light-years away is extraordinarily difficult to measure. Van der Marel's team used Hubble to track the positions of individual stars in Andromeda over a period of 5 to 7 years. By comparing images taken years apart, they measured the transverse motion of the galaxy with enough precision to answer the question. Andromeda is not going to miss. It is aimed directly at the Milky Way. The closure speed is roughly 110 kilometers per second. The estimated time to impact is approximately 4.5 billion years. This is not a hypothesis. It is astrometry. The measurements have error bars, but the central conclusion is firm. 2 galaxies, each containing hundreds of billions of stars, are falling toward each other on a collision course that has been set since the moment their mutual gravity first took hold. Andromeda is roughly 1.5 times the mass of the Milky Way. This is not a merger of equals. It is an absorption. The result has already been named Milkomeda, an elliptical galaxy formed from the wreckage of 2 spirals. The merger will take approximately 2 billion years to complete, and during those 2 billion years, the internal structure of both galaxies will be rewritten from the ground up. 4.5 billion years is a comfortable number. It is roughly the remaining lifespan of the Sun. By the time Andromeda arrives, the Earth may already be uninhabitable for other reasons. So why does this collision matter? because of what happens to things caught inside a galactic merger. And the physics of that process is not gentle. When two galaxies collide, the stars almost never hit each other. The distances between stars are so immense that even in a direct collision of two spiral galaxies, the probability of any two stars physically touching is essentially zero. Stars pass through the gaps like two swarms of bees flying through each other. But gravity does not need contact. It needs proximity. And proximity in a merger is guaranteed. Van der Marel's simulations, built on the Hubble measurements, track the probable fate of the Sun's orbit through the merger. The results are statistical, not deterministic, but the probabilities are specific. There is approximately a 12% chance that the solar system will be ejected from the merged galaxy entirely, flung outward by a gravitational slingshot as the cores pass through each other. There is a 2.7% chance that the Milky Way's outer disk, where we live, will be captured by one of Andromeda's tidal tails before the merger is even complete, pulled away like a thread unraveling from a sweater. In either case, the destination is intergalactic space, not the outskirts of a galaxy, not a quiet suburb. The void between galaxies, no gas clouds to form new stars, no neighboring systems within millions of light years. The night sky would be empty, not dark with scattered stars. Empty. A black canvas with a faint smudge of the receding merger millions of light years behind you. No return, no rescue, no neighbors. The loneliest possible outcome for a solar system that spent its entire existence inside a crowded spiral arm. A 12% chance of permanent exile into absolute nothing. Not a bad day. An eternity of silence. So the galaxy is heading for a collision that cannot be avoided. Stars will be scattered. Some will be thrown into the void. The timescale is billions of years, long enough to feel like someone else's problem. But there is a force already acting on every galaxy, every cluster, every cubic meter of space in the observable universe. It was discovered 26 years ago. It accounts for 68% of the total energy content of everything that exists. And we have no idea what it is. In 1998, two teams working independently made the same discovery at the same time. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees. Both teams were using Type 1 supernovae as standard candles, objects whose intrinsic brightness is known, to measure how fast the expansion of the universe is slowing down. Gravity pulls matter together. After the Big Bang, the expansion should have been decelerating, like a ball thrown upward gradually losing speed. But the supernovae were too dim, dimmer than they should have been at their measured distances, which meant they were farther away than the decelerating model predicted, which meant the expansion was not slowing down, it was speeding up. The universe is not coasting after the initial push. Something is pressing the gas pedal. Both teams published. Both teams checked each other's data. The result held. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize in Physics. The name assigned to the unknown force was dark energy. It was not a discovery in the normal sense, it was a label on a hole in the map. 68% of the energy budget of the cosmos is something that pushes space apart, and we do not know its nature, its origin, or its future behavior. We measure its effect. We do not understand its cause. Not understanding dark energy would be acceptable if its behavior were constant. A steady push, the same force per unit volume of space, would mean the expansion accelerates, but at a predictable rate. Galaxies drift apart. Eventually the night sky goes dark. The universe fades in a slow, quiet way. That is the default model. Lambda. CDM. A cosmological constant. Unchanging, manageable, bleak, but stable. But in 2003, Robert Caldwell at Dartmouth College published a scenario that removed the word stable from the equation. He asked a specific question. What if the dark energy is not constant? What if it is getting stronger? In cosmology, the behavior of dark energy is described by a single parameter called W. If W equals exactly -1, dark energy is a cosmological constant, steady, predictable. If W is greater than -1, dark energy weakens over time and the expansion eventually slows. If W is less than -1, dark energy strengthens. The expansion does not just accelerate, it accelerates exponentially. And the math of that exponential is a countdown to total dissolution. Caldwell called the scenario the Big Rip, and he calculated the timeline. Approximately 200 million years before the end, the expansion becomes strong enough to overcome the gravitational binding of galaxy clusters. Galaxies fly apart. 60 million years before the end, individual galaxies disintegrate. Stars are pulled from their orbits. 3 months before the end, solar systems break apart. Planets leave their stars. 30 minutes before the end, the expansion operates at the atomic scale. The Earth comes apart. A fraction of a second before the end, atoms themselves are split open. Nuclei separate. The fabric of matter ceases to exist. The current best measurement of W comes from the Planck satellite, supernova surveys, and baryon acoustic oscillation data. The value is approximately -1.03 plus or -0.03. The cosmological constant sits at -1. The phantom threshold, the point where the Big Rip becomes inevitable, sits at anything below -1. The measured value is below -1, inside the error bars, not confirmed, not ruled out. The difference between a universe that expands forever in cold silence and a universe that separates every atom in existence sits within the margin of error of our best instruments. But even if dark energy behaves itself, even if you sits at exactly -1 forever, the universe still has an ending. It is not dramatic. It is not sudden. It is the slowest, quietest, most thorough form of termination that physics can describe. And it is guaranteed by the same law we met in your body. The second law of thermodynamics, entropy, applied not to a cell or an organism, but to everything. In 1852, William Thomson, later Lord Kelvin, published a short paper with a title that read like a eulogy, on a universal tendency in nature to the dissipation of mechanical energy. The argument was simple. If entropy always increases, if every process converts useful energy into waste heat, then the universe is running down, like a fire burning through its fuel, like a battery draining without a charger. Eventually, there will be nothing left to burn. The timeline is not vague. Astrophysicists have mapped it. Star formation will continue for roughly another 100 trillion years, 10 to the 14th, as remaining gas clouds collapse. After that, no new stars ignite. The last red dwarfs, the slowest burners, will exhaust their hydrogen and fade. White dwarfs, the cooling embers of spent stars, will radiate their residual heat into space over the next 10 to the 15th years, and go dark. If grand unified theories are correct, and protons decay, then all baryonic matter, every atom that ever formed a planet or a person, will dissolve into leptons and photons over roughly 10 to the 40th years. The last holdouts are black holes. They evaporate through Hawking radiation, a process of quantum tunneling at the event horizon that leaks energy particle by particle. The most massive black holes in the universe will take roughly 10 to the 100th years to fully evaporate. That number is a 1 followed by 100 zeros. After that, the universe contains nothing but photons and leptons drifting apart in a space that continues to expand. No gradients, no structure, no processes. The temperature approaches absolute zero, but never quite reaches it. Nothing happens. Nothing can happen. Not ever again. So the universe runs down. Stars fade, matter dissolves, black holes evaporate. The timeline stretches across numbers so large they stop meaning anything to a human brain. But the thermal equilibrium is not just an ending. It is an erasure. And the physics of that erasure is precise. In 1961, a physicist at IBM named Rolf Landauer published a result that sounds like information theory but is actually thermodynamics. Landauer's principle states that erasing one bit of information, a single yes or no, a single 0 or 1, requires a minimum energy expenditure of kT times the natural logarithm of 2, where k is Boltzmann's constant and T is the temperature. This means information is not abstract. It is physical. It has weight. It takes energy to create and energy to erase. A memory stored in the synapses of your brain is not a metaphor. It is a thermodynamic state. This makes the final equilibrium personal. Everything humanity has ever created is information. The structure of the pyramids is information. The sequence of notes in a symphony is information. The memory of your mother's face is information. The data on the Voyager Golden Record is information. In a universe approaching maximum entropy, all of this degrades, not because someone wrecks it, because the physics that maintains it runs out of energy. The pyramids will erode. The Voyager probe will be hit by micrometeoroids and cosmic rays until the golden record is unreadable. The atoms that carried the information will decay if protons are mortal. The photons that scattered off those atoms will redshift towards zero energy as the universe expands. Every trace, every echo, every residual pattern that might indicate something once existed here will be diluted into thermal noise, indistinguishable from the background of empty space. The universe will not remember that we were here. It is worse than that. The universe will reach a state in which the concept of remembering is physically impossible. There will be no gradients to store data, no structures to process it, no energy to read it. The hard drive is not just wiped. It is melted down and spread evenly across an infinite floor. The information does not go somewhere else. It becomes nowhere. So the universe ends everything, erases the evidence, and runs the clock until nothing can ever happen again. But all of this assumes something we rarely question: that the clock runs in one direction, that time moves forward, that the past is behind us and the future is ahead. This feels so obvious that it barely seems worth mentioning. And yet, when you open the equations, the arrow is not there. Every fundamental law of physics is time symmetric. Newton's laws of motion work the same whether you run them forward or backward. Maxwell's equations of electromagnetism do not care which direction time flows. The Schrödinger equation, the master equation of quantum mechanics, evolves identically in both directions. Einstein's field equations of general relativity contain no preferred arrow. If you filmed any fundamental interaction, any collision between particles, any electromagnetic wave propagating through space, and played the film in reverse, the physics would be perfectly valid. The reversed version obeys all the same laws. Nothing in the mathematics distinguishes past from future. And yet, eggs break and never reassemble. Coffee cools and never reheats. People age and never grow younger. The world has a direction. We feel it in every cell of our bodies. We build our entire civilization on the assumption that causes precede effects. But the deepest equations we possess do not contain this assumption. The arrow of time is not written into the laws, it is emergent. In the 1870s, Ludwig Boltzmann proposed the answer that most physicists still accept. The arrow of time is the direction of increasing entropy. Time flows the way disorder grows. We do not perceive the future because it is written somewhere. We perceive it because it is the direction in which the number of possible arrangements of matter increases. The past feels fixed because there were fewer ways to arrange things. The future feels open because there are more. This means something unsettling about the nature of your experience. You do not live in time, you live in the gradient of entropy. Your sense of before and after, your memory, your anticipation, your feeling that this moment is moving, all of it is a byproduct of disorder increasing around you. Time is not a river carrying you forward. Time is the universe falling apart, and your brain interpreting the fall as a direction. So time is not a fundamental feature of the universe, it is a side effect of things falling apart. But there is a deeper rule that physicists hold even more sacred, than the arrow of time. Unitarity. The principle that information is never erased. If you burn a book, the information in it is not lost. It is scattered into ash, smoke, light, and heat. Theoretically, if you captured every particle produced by the blaze and reversed their trajectories, you could reconstruct the book. The information is scrambled, but not gone. Unitarity says the universe keeps perfect records. Nothing is truly forgotten. In 1974, Stephen Hawking broke this rule. Hawking had been studying black holes, the ultimate gravitational traps. Nothing that crosses the event horizon can return. Light cannot escape. Matter cannot escape. The interior of a black hole is a one-way door. But Hawking applied quantum field theory to the curved space-time near the horizon and discovered something no one expected. Black holes are not completely black. They radiate. The mechanism is subtle. At the boundary of the event horizon, quantum fluctuations constantly produce pairs of virtual particles. Normally, these pairs annihilate each other instantly, but at the horizon, one particle can fall in while the other escapes. The escaping particle carries energy away from the black hole. Over immense timescales, the black hole loses mass. It shrinks. Eventually, it evaporates entirely. The problem is the nature of the irradiation. Hawking radiation is thermal. It is random. It carries no information about what fell into the black hole. When a star collapses into a black hole, it carries with it a complete physical history. The mass, the composition, the spin, the structure of every atom. When the black hole evaporates, that history is radiated away as featureless noise. The information is not scrambled, it is gone. This means either Hawking is right and unitarity is broken, the universe does not keep records, information can be permanently erased, or Hawking is wrong and the radiation somehow encodes the information in a way we do not understand. Both options are catastrophic for physics. One breaks quantum mechanics, the other breaks our understanding of gravity, and for 50 years, nobody has found a resolution that satisfies both. For decades, the information paradox was treated as a deep but distant problem. Black holes evaporate slowly. The timescales are so enormous that most physicists assumed the answer would emerge eventually. Somewhere in the marriage of quantum mechanics and general relativity that we have not yet achieved. It was a puzzle for the next generation. Then, in 2012, 4 physicists at the University of California, Santa Barbara, set the puzzle ablaze. Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully published a paper known by their initials, AMPS. They did not solve the paradox. They proved it was worse than anyone thought. Their argument was precise. Start with 3 assumptions, each of which is a pillar of modern physics. First, unitarity. Information is preserved. Second, the equivalence principle from general relativity. An observer falling through the event horizon of a large black hole notices nothing special at the crossing. No wall, no barrier, just smooth space-time. Third, quantum field theory is valid in the vicinity of the horizon. AMPS proved that these 3 statements cannot all be true simultaneously. If you demand that information escapes the black hole, and if you demand that quantum field theory holds near the horizon, then the math requires a wall of infinite energy at the event horizon. A firewall. An observer falling in would not drift smoothly through. They would be disintegrated at the boundary. But this violates the equivalence principle. General relativity says the horizon is not a special place. There should be nothing there to harm you. You cannot have all 3. At least one pillar of physics must be wrong. Not adjusted, not extended, wrong. This is not a technicality. Quantum mechanics, general relativity, and quantum field theory are the 3 frameworks on which all of modern physics is built. Every experiment we have ever run confirms all 3 within their domains. And AMPS showed that at the boundary of a black hole, they are mutually exclusive. The foundation of physics is not just cracked, it is self-contradictory. We built 3 walls and discovered that where they meet, they cannot all stand. So the framework we use to describe reality is internally broken. The 3 theories that have passed every experimental test we have ever designed fail when they meet at the edge of a black hole. But there is an older problem, quieter, less dramatic, and in some ways, more disturbing. Because it does not ask whether physics is broken, it asks why physics works at all. The strong nuclear force holds protons and neutrons together inside the atomic nucleus. Its coupling constant, alpha sub s, is approximately 0.1. That is not a derived value. It is a measured one. Nobody knows why it is 0.1 and not 0.2 or 0.05. It is a free parameter of the standard model. A knob that could, in principle, be set to any value. But the consequences of turning that knob are absolute. Increase alpha sub s by 4%, and the diproton becomes a stable particle. 2 protons bind together without a neutron. This means hydrogen fuses instantly in the cores of stars, instead of through the slow chain reaction that powers the sun. Stars burn out in millions of years, instead of billions. Chemistry never gets started. Decrease alpha sub s by 4%, and deuterium becomes unstable. The first step in stellar nucleosynthesis fails. Stars cannot forge heavy elements. No carbon, no oxygen, no silicon, no planets. Gravity. The gravitational constant must be tuned to within 1 part in 10 to the 40th for stars to exist. Too strong, and every gas cloud collapses directly into a black hole. Too weak, and matter never clumps. Stars never ignite. Galaxies never form. The cosmological constant, the energy density of empty space, measured at approximately 10 to the minus 122 in natural units. In 1987, Steven Weinberg, before the value was experimentally confirmed, calculated that if the cosmological constant were positive and larger than its actual value by a factor of roughly 100, gravitational attraction would be overwhelmed on galactic scales. Galaxies would fly apart before stars could form. If it were negative by a comparable amount, the universe would have recollapsed within a few million years of the Big Bang. Every one of these numbers sits in a narrow band. Step outside the band in any direction, and the universe does not produce complexity. No stars, no chemistry, no life, no observers. The dials are set, and nobody left a note explaining who set them or why. The numbers are set. The margins are thin. But perhaps this is just how the universe happens to be. Perhaps there is no mystery. Perhaps asking why the constants have these values is like asking why the speed of light is what it is. It just is. Not everything needs an explanation. Except that in 1953, a British astrophysicist demonstrated that the fine-tuning is not passive. It is suspiciously specific. Fred Hoyle was working on the problem of carbon synthesis inside stars. The standard pathway, called the triple alpha process, requires 3 helium nuclei to fuse into 1 carbon-12 nucleus. But the probability of 3 particles colliding simultaneously is vanishingly small. Without a boost, the universe would produce almost no carbon. And without carbon, there is no organic chemistry, no DNA, no proteins, no life. Hoyle reasoned backward from the fact that carbon exists. If carbon is abundant, the triple alpha process must have a resonance, a specific energy level inside the carbon-12 nucleus that amplifies the reaction rate by orders of magnitude. He predicted the energy level at 7.65 mega-electron volts. He told the nuclear physicists at Caltech what to look for. They found it within 1% of his prediction. A physicist to deduce the internal structure of an atomic nucleus from the observation that human beings exist. The logic ran backward through the entire chain. We are here, therefore carbon is abundant, therefore the reaction is amplified, therefore a resonance exists at a precise energy. And it did. Hoyle himself was disturbed by the result. He wrote that a common-sense interpretation of the data suggests that a super-intellect has monkeyed with the physics. He did not mean this religiously. He meant it as a statement about the improbability. The constants are not just permissive of complexity. They are engineered for it, down to resonance levels inside individual atomic nuclei. The standard scientific response is the anthropic principle. We observe a universe with these constants because in a universe with different constants, there would be no observers. This is logically airtight. It is also not an explanation. It is a tautology. It answers, why do we see these numbers? With, because you are here to see them. The question of why these numbers and not others remains open. The dials are set. The note is still missing. And the precision is too sharp to feel like an accident. So the constants are set to values that produce complexity, and no one can explain why. The anthropic principle says we are here to ask the question only because the answer permits our existence. It sounds circular because it is. But there is a version of that circularity that goes much deeper. And it leads to a conclusion that most physicists find genuinely horrifying. In 1896, Ludwig Boltzmann proposed a thought experiment to explain why the universe has low entropy, why it is ordered at all, when the most probable state of any system is maximum disorder. His suggestion was that the observable universe is a random fluctuation, a brief dip in entropy in an otherwise featureless cosmos. We happen to live during the dip. In 2004, Andreas Albrecht and Lorenzo Sorbo at UC Davis took Boltzmann's idea and followed it to its logical endpoint. If the universe exists for an infinite amount of time in a state of high entropy, then random quantum fluctuations will eventually produce any configuration of matter, including a brain. A single brain, complete with neurons, synapses, and a full set of false memories, assembling spontaneously out of the vacuum. It would flicker into existence, experience a single moment of consciousness, and then dissolve back into noise. This is not a joke. It is a statistical argument, and the statistics are staggering. In an infinite universe, the number of these so-called Boltzmann brains, produced by random fluctuation, is infinitely larger than the number of brains produced by normal evolution on normal planets, around normal stars. Real observers with genuine histories and genuine environments, are infinitely outnumbered by hallucinating chunks of matter that assembled by accident. If you accept this math, and no one has found a flaw in it, then the most probable explanation for your current experience is not that you are a human being on a planet in a galaxy that formed over billions of years. The most probable explanation is that you are a momentary fluctuation in the void. Your memories of childhood, of yesterday, of the beginning of this sentence, are not records of events. They are patterns that happen to crystallize in the noise. You did not grow up. You appeared. And you will vanish in a fraction of a second. The only way to escape the Boltzmann brain problem is to prove that the universe is not eternal, that it has a finite past, a finite future, and a total entropy budget that does not allow infinite time for fluctuations. In other words, the only way to guarantee that you are real is to guarantee that the universe ends. So the Boltzmann brain problem says you are probably not real unless the universe has an expiration date. One way or another, the question of whether your experience is genuine keeps circling back to the same uncomfortable territory. And in 2003, a philosopher at Oxford formalized that discomfort into an argument that has no obvious flaw. Nick Bostrom published a paper called "Are You Living in a Computer Simulation?" The argument is not mystical, it is not science fiction. It is a trilemma, a logical structure with exactly 3 possible conclusions. At least one of the following must be true. 1. Almost all civilizations at our level of development go extinct before reaching the computational power to simulate consciousness. 2. Almost all civilizations that reach that level choose not to run simulations of conscious beings. 3. We are almost certainly living inside a simulation. The logic is statistical. If even a small fraction of advanced civilizations run detailed simulations of their ancestors, then the number of simulated conscious beings vastly exceeds the number of biological ones. By the same counting argument that makes Boltzmann Brains probable, the simulated minds outnumber the real ones by orders of magnitude. And if you cannot tell the difference from the inside, the probability that you are one of the rare originals rather than one of the countless copies is vanishingly small. In 2012, a team at the University of Bonn, Silas Bean, Zohre Davoudi, and Martin Savage proposed a concrete experimental test. If the universe is simulated on a discrete lattice, a grid with finite resolution, then the behavior of the highest energy cosmic rays should show a signature. Specifically, the distribution of arrival directions should be anisotropic, aligned with the axis of the lattice. The cosmic rays would prefer to travel along the grid lines, like cars on city streets rather than hikers on open terrain. The test has not been conclusively performed. The required energy levels are at the extreme edge of observational capability. But the proposal exists, it is specific, it is falsifiable. And the fact that physicists can seriously propose a test for whether reality is computed tells you something about where the boundary between physics and philosophy now sits. It sits nowhere. The two have merged, and neither one is offering reassurance. So the question of whether reality is real has moved from philosophy into the laboratory. But long before Bostrom or Boltzmann Brains, quantum mechanics was already telling us that reality does not behave the way it should. That the act of observation is not passive. That looking at the universe changes the universe. And that the role of the conscious observer in physics is not a footnote. It may be the central problem. In 1935, Erwin Schrödinger proposed a thought experiment designed to make the Copenhagen interpretation of quantum mechanics look absurd. Place a cat in a sealed box with a radioactive atom, a Geiger counter, and a vial of harmful substance. If the atom decays, the counter triggers, the vial breaks, and the cat perishes. If the atom does not decay, the cat lives. According to the quantum mechanics, before anyone opens the box, the atom is in a superposition of decayed and not decayed. And since the cat's fate is linked to the atom, the cat is in a superposition of alive and not alive. Simultaneously both, neither one nor the other. Schrödinger meant this as a reductio ad absurdum. It was supposed to show that quantum mechanics must be incomplete, but every experiment since has confirmed that superposition is real. Particles genuinely exist in multiple states until measured. The cat scenario is absurd only because cats are large. At the scale of individual particles, this is standard operating procedure. In 1978, John Archibald Wheeler pushed the problem further. He designed a thought experiment called the delayed choice experiment. A photon is sent at a barrier with two slits. After the photon has already passed through the slits, the experimenter chooses whether to detect which slit it passed through or whether to look for an interference pattern. The choice is made after the photon has already traveled, and yet the photon's behavior conforms to the choice. If you look for interference, the photon behaves as a wave. If you look for which path information, it behaves as a particle, as if it knew what you were going to do. In 2007, a team led by Alan Aspect's group, Vincent Jacques and collaborators, performed the experiment with single photons and fast random switching of the detector configuration. The result confirmed Wheeler's prediction. The observer's choice in the present appears to determine the photon's behavior in the past. Reality is not sitting there waiting to be seen. It is being assembled by the act of seeing. So the observer is not a spectator. The observer participates. The act of measurement shapes what is measured. But this creates a problem that has plagued quantum mechanics since its founding. If everything is in superposition until observed, why does the world look solid? Why does the table stay a table when you leave the room? Why do we all agree on the same reality? If observation is the key, and each of us observes slightly differently, why is there a shared world at all? In the early 2000s, Wojciech Zurek at Los Alamos National Laboratory proposed a framework that redefines what objectivity means. He called it quantum Darwinism. The idea is elegant and deeply strange. When a quantum system interacts with its environment, and every system does constantly, information about the system's state is copied into the surrounding particles. Photons scatter off the table and carry information about its position. Air molecules bounce off it and carry information about its temperature. The environment acts as a witness, recording copies of certain quantum states and discarding others. The key insight is selection. Not all quantum states get copied equally. Some states are robust. They survive the process of being copied into the environment without being distorted. Others are fragile. They decohere, smear out, and vanish before they can leave a trace. The states that survive, the ones that get copied into millions of environmental particles, are the ones we see. They are the ones that become classical reality. This is natural selection applied to information. The table looks solid because the quantum state corresponding to a solid table is the one that reproduces itself most efficiently into the photons hitting your retina, the air molecules touching your hand, the gravitational field you measure with your instruments. The table is not objectively there in the old-fashioned sense. It is the winning state, the one that outcompeted every other possible quantum configuration in the race to imprint itself on the environment. Reality is not a fact, it is a survivor. The world you see is the version that was best at copying itself, and every version that lost the competition is gone, not hidden, not stored somewhere in a parallel branch, decohered, dissolved into noise. The universe is running a tournament every nanosecond, and you only ever see the champion. So, here is where we are. At the smallest scale, the foundation of matter is not solid. It is a cloud of probabilities held together by forces that have no obligation to be permanent. The proton may be fading. The vacuum may be false. A quantum fluctuation could rewrite the laws of physics in a bubble expanding at the speed of light, and you would never see it come. At the scale of your body, 40,000 DNA lesions hit every cell every day. The repair system is ancient and imperfect. The telomeres shorten with every division, and the enzyme that could stop the clock is locked away. The only cells that use it are the ones trying to shut you down. Entropy runs underneath all of it, pulling every structure toward dust, and the arrow of time guarantees the pull never reverses. At the scale of the planet, the magnetic shield is weakening and may be preparing to flip. The sun discharges on a schedule written in tree rings, and the last major event was 12 centuries ago. More than half the asteroids large enough to end a city have not been found. The ground beneath Yellowstone has erupted 3 times at intervals that suggest we are statistically overdue. At the scale of the galaxy, gamma-ray bursts can sterilize a planet from thousands of light years away. 100 million invisible black holes drift in silence, and we have found exactly one. Andromeda is falling toward us at 110 kilometers per second, and there is a 12% chance our solar system gets thrown into the void. At the scale of the universe, dark energy is pulling space apart, and the parameter that determines whether it stops or accelerates through every atom sits within the margin of error of our instruments. The final equilibrium will erase not just life, but the evidence that life ever existed. The information paradox says our best theories contradict each other at the edge of a black hole. The constants are tuned on a razor with no explanation. And the deepest layer of physics says reality itself is not a fixed stage, but a competition that your version of the world happens to be winning. For now, every one of these timers is running, right now, simultaneously. Not sequentially, not politely waiting in line. All of them, at once. And yet, you are here, right now, reading this sentence with eyes that evolved over 500 million years from a patch of light-sensitive cells on a worm, breathing air that was manufactured by cyanobacteria 2.5 billion years ago, sitting on a rock that has survived 4.5 billion years of bombardment, volcanism, ice ages, and mass extinctions without once becoming permanently uninhabitable. The protons in your body have not decayed. The vacuum has not tunneled. The gamma-ray burst has not arrived. The sun has not discharged its worst. The asteroid has not come from the blind side. Yellowstone is asleep. The magnetic field, weakened as it is still holding. Andromeda is 4.5 billion years away. The dark energy has not crossed the phantom threshold. And the information that makes you you, the synaptic patterns, the molecular structures, the quantum states that encode your memories and your thoughts, and your sense of being a person, they are still intact, still coherent, still running. Every second that passes is a second in which none of these mechanisms activated. Every heartbeat is a statistical miracle, not because heartbeats are rare, but because the conditions that allow a heart to exist at all are balanced on the edge of a razor so thin it cannot be expressed in numbers that fit on a page. Roger Penrose's number, 1 in 10, to the power of 10, to the power of 123. That is the probability of the initial conditions that led to this moment, and you are inside it. Not watching from a distance. Inside. A configuration of matter so unlikely that the universe will never produce it again, after the final equilibrium erases the last trace of structure. You are a one-time event. Every anxiety you carry, every regret, every late-night worry about money or status, or whether you said the wrong thing at a dinner party, exists inside this window. This absurdly narrow, statistically impossible, cosmically brief window in which atoms can hold together and brains can process, and someone can sit in a room and feel the weight of being alive. The scale of what we have covered makes one thing absolutely clear. You do not control any of it. Not the vacuum, not the entropy, not the sun, not the field, not the constants, not the dark energy, not the arrow of time. None of it asked your permission before it started. None of it will ask your permission before it ends. And that is the point. If the vacuum decays, you will not see the bubble. If a gamma-ray burst reaches us, you will not hear it coming. If the cosmological constant crosses the phantom line, you will not feel the separation until there is nothing left to feel with. These are not risks you can manage. They are not problems you can solve. They are the architecture of reality itself. And the architecture does not negotiate. Which means the one thing you were never told, the one thing that every anxious thought in your head refuses to accept, is that you are free. Not free because you earned it. Not free because you figured it out. Free because there is literally nothing you can do about any of this. The weight you carry around, the pressure to perform, to succeed, to matter, to leave a legacy, exists inside a window that will close whether you perform or not. The mortgage, the career, the argument you had last week, the email you forgot to send. None of it registers on any scale that the universe operates on. You are a chemical accident that woke up. You opened your eyes inside a structure so unlikely that the number describing its probability has more digits than there are atoms. You got to see stars. You got to feel weather. You got to sit across from another person and know what it is like to be known. Every civilization that might have existed before you was either filtered out or erased. Every configuration of matter that will exist after you will never reassemble into this exact pattern. You are not a rough draft. You are not a stepping stone to something better. You are not a footnote in the margin of a cosmic process that does not care. You are the process looking at itself for one unrepeatable moment. So stop worrying about the abyss. The abyss is not going anywhere, but this second is, and you are in it. You are here. That is enough. That has always been enough. Now go enjoy it.